Hey, this is a short video on problem 1353 and 1354. So for here, we're given a car that travels around a circular path given a specific radius, tilted on an angle of 20 degrees. And we know this coefficient of static friction to be 0.2. So let's answer these questions. So first, we have to determine the maximum constant speed the car can travel without sliding up the slope. Okay, so for this, we have to consider what does it mean to travel at maximum constant speed. So when you move at a really fast speed, then you have to have a really large centripetal force pushing you into the center of the circle in order for the car to move in the center of the circle. And so this force is given by acceleration times the mass. So we know this acceleration is v squared over rho, and rho represents the radius. And so therefore, the force, centripetal force, towards center circle has to be equal to mv squared over rho. If this is not met, then the car can no longer move in centripetal motion, that is to move around the circle. And in this problem, there are only two forces that push the car to the center of the circle or provide this centripetal motion. So here is a diagram showing the bird's eye view of the car's trajectory, which is around the circle, and here's a side view. This is angle 20 degrees. Let's see. So here's an example of the car going around in a circle without the tilt of 20 degrees. So just a flat circle. In this case, the only force that causes the car to go in the circle will have to be friction force, as that pushes inwards. There's no other force that can keep the car into the center circle. As the car is moving, tilting, moving and rotating in a circle, the only force that keeps it moving that way will only be friction. In this example, the car is tilted at an angle and driving along a bank. And so therefore, there's two forces creating this centripetal motion. One is the normal force, and the second one is the friction force. And only the components of those forces that act towards the center will be the centripetal force contributing to the centripetal motion. So we only really have to worry about Fn sine theta and the friction force that goes inwards. And of course, you gotta consider the other ones too, because they have to balance in equilibrium. So if we can see, next we have data of the problem. So we're given mass, gravity, the angle of the bank, radius, which is rho, and mu, 0.2. So here's the acceleration. The u sub n denotes the unit vector towards the center of the circle. So the acceleration is v squared over rho. And here are the forces. And we can ignore the fourth equation, is not important. Fourth equation, this equation here, is for the second part of the problem. So we're only worried about just the first, ignore the fourth one, so just the first three equations. This here, we have a force of gravity pointing downwards. As seen from the diagram, force of gravity is mg, and it points downwards. That's why it's negative mg. Let's see, we have normal force and friction force. So normal force is n sine theta un, and cosine theta upwards. So let's see here, n sine theta un. If you can see from this diagram, here's this angle here. It's equivalent to this angle as well. And the part that moves inwards is going to be sine of this angle times the normal force. And the part that moves up is just the cosine of this angle times the normal force. So they just written as a whole thing as part y in this diagram, and then part x here. Okay, now you might be wondering, how do they get the friction force? So the friction force will be a little bit different. So ignore the other one. Okay, yeah. So the friction, okay, so to explain why the friction is going inwards, so because the we're finding maximum speed. As the speed gets larger and larger, there has to be more force required to push the car into centripetal motion. And so the car would actually, without enough force, the car would actually try to go out of this circle because there's not enough force keeping it inside the circle. So there would be enough acceleration to push the car inwards. So it would likely go out of the circle if there's not enough. And so therefore friction is keeping the car into centripetal motion as well as the normal force. And so that's why the friction is pointing into the circle. Here's a diagram to show this. Let's see if I can find it. This is not right. What's this? Okay, then here it is. This might be a little bit messy. Yeah, so you have a friction force that's pushing the car inwards here along this direction downwards. And so this angle is equivalent to this angle, which is equivalent to this angle. And so by this diagram, you can see that there is friction will be acting into the center of a circle and downwards. So going all the way back into the center of the circle and downwards. So yes, it matches with these here. Negative cosine theta un and sine theta k. Oh, no, this is the wrong one. Okay, this one, positive. Yeah, it's supposed to be positive because it's going in the center circle and it's going downward, so this is negative, so ignore that equation. So now that we got the forces, we got gravity, the normal force, and the friction force, ignoring the fourth one for now, we get these equations here. So all we have to do is just sum up the forces that go into the circle and then sum up the forces that go in the y direction, up and down, for this one. So up and down into the circle. So if we do that and add the components that go into the circle, which is this and this, you get this, and this has to be these forces have to provide the centripetal force, which is mv squared over rho. And the second equation is just that you have the forces acting in the up and down direction. So there's this one here, so this times this, and this times this. So these three will have to be 0 because it's at equilibrium. The car is not going to fly up and fly down. It's just going to stay there, but it will move in a circle. And so to get to this step, we did that. And now to proceed, here we factor out n. First we factor out n from the first equation, factor n out. We move mg to the other side, and then we factor out the n from here. If you do that, then divide both equations. This equation divide by this equation. So that would be sine plus cosine over cosine minus sine. And if you move this to the other side and divide this with this, so pretend this is on the other side, so this divided by this will be v squared over p over g. So that gets you to here. Ignore the second one, so this is not important. So if you plug in values, you get 24.4. However, you might want to simplify it a little bit more. So we have this from earlier, and then you might want to know how this simplifies to this. It's a trigonometric identity, and this also simplifies to this. To know more on this, maybe I can just do a simple proof. So let me just write it out really quick. So you have sine, I'm going to treat theta as a, and they also define the coefficient of friction as tangent of another angle. So let's just call that tan of b, because those two angles the symbols look too similar. So you have sine a plus sine a plus tan b cosine a all over cosine a minus tan b sine a. So this looks like this. And if you just simplify this even more, so tan b is equivalent to sine b over cosine b. So I'm just gonna rewrite what I have there. So it's hard to see. Okay, so just give me a moment here. Okay, let's see here. So yeah, just give me a second. Cosine a cosine. Okay. Shoot. Yeah, so all I did was just break up the tangent into the sine and cosine parts. And now let me multiply both top and bottom by cosine of b. So I get d sine a plus, no, sine a cosine b plus sine b cos a over cos a sine, no, wait, sorry, yes, I multiply this by this, and then I get cos b minus sine b sine a. So if I multiply both sides by both the top and bottom by cos of b, then what I should get is something like this. So top here, this simplifies to this. Multiply top and bottom by cos b simplifies to this. So you have sine a cos b plus sine b cos a cos b minus sine b sine a. And so what you might recognize from here is trig identity. So how should I say? Okay, looky here. Here are some angles, some different identities that you might know. Sine and cosine plus sine b cosine a, so sine a b. Okay, it's not the first one. It must be the, wait, is it the first one? Okay, it seems like, yeah, it is the first one. So you have sine theta plus this. So this is your top. Your bottom one looks to be this here. So if I replace the top with this and divide by the bottom, which is this, gives me tan of theta plus this. And this is another trig identity thing. You can probably find it on Khan Academy. So this fraction here simplifies to sine of a plus b over cosine of a plus b, like this. And so this is just equal to tan of a plus tan of a plus b. Yep, so that's how they got this. And you can just replace this whole thing with this. And solving for v will give you this expression here. And that's how you solve that. Okay, so moving on. Second part should be really easy. Determine the minimum constant speed the car can travel without sliding down the slope. So this time, the car is not moving as fast. So because the car is not moving as fast, you can expect the car to, there won't be really as much friction pushing the car into the circle as the car moves slower and slower. And there's just a point where the car just starts to slide down the slope, because the only centripetal forces causing this motion will be friction and normal force. And friction increases as the car moves faster and faster. So there must be a point where the car can just, there's no more friction force pushing the car inwards. And so we can ignore this one for this problem. So ignore this one. So I have the top, these two equations are standard, but this time friction is pointing up the bank. because it's preventing the car from falling in. And so if you work that out, you get that this is acting in the opposite direction, so that's why the signs are switched. And applying the same logic, you arrive at this equation, not this one, this equation, and solving that will give you this. And then by applying the same steps as before, if you take this and just did whatever I did before to reduce, this reduces to tan of a minus, so a minus b, not a plus b this time, a minus, and then solving for v will give you this expression here. And this, from here you can just easily solve for velocity. And yeah, I think that's it. I hope that kind of helped. And hopefully we'll do another problem or something like that. I'm not sure, but yeah.